Hey everyone, welcome back to the channel. So if you're a data engineer preparing for SnowPro Core COF-C03 exam and trying to level up your cloud knowledge, this video is for you. Because today we're going through 6 practice questions, real exam quality questions that cover some of the most tested and most misunderstood topics in the Snowflake ecosystem. We're talking about security roles, stage replication, materialized views, notebook runtimes, Snowsight monitoring, and virtual warehouse performance tuning. That's a lot of ground to cover, so let's make sure we do it right. Let's look into the first question, and we're starting with something that a lot of people find confusing the first time they encounter it: Snowflake's account usage roles. Question 1 is a multiple choice, one correct answer. Here it is. Which role controls security-related account usage views? There is one correct answer, and here are your 4 options to choose from. Option A, Object Viewer. Option B, Governance Viewer. Option C, Security Viewer. Option D, Usage Viewer. Take a moment, read those 4 options again. If you know Snowflake's role model well, this might feel obvious, but if you're newer to it, all 4 of those names sound like they could be plausible answers. So think it through before we go further. Pause the video here, think, and choose the right answer. Okay, let's break that down together. And I want to start by giving you a little bit of context on why Snowflake even has these different viewer roles. Because once you understand the why, the answer basically reveals itself. So here's the deal. The account usage schema in Snowflake is a goldmine of information. It contains views that give you visibility into basically everything happening inside your Snowflake account. Login history, query history, billing and credit usage, policy definitions, object metadata, you name it. It's incredibly powerful. But that power comes with responsibility, because not everyone should have access to all of it. Think about it from a real enterprise perspective. Your data engineers probably need to see query history and warehouse performance data. Your compliance and legal team needs to see login history and access patterns for audit purposes. Your FinOps team needs to see credit consumption, but should your compliance team be digging through billing data? Should your FinOps team be able to see which specific users logged in and when? Probably not. You want to give each group exactly the access they need, no more, no less. That's the principle of least privilege, and it's the whole reason Snowflake created these separate viewer roles. Now, with that context, let's walk through the options. Option A, Object Viewer. This role is specifically about object metadata. We're talking about databases, schemas, tables, columns, the structural skeleton of your Snowflake environment. If someone needs to understand what objects exist in the account and how they're organized, Object Viewer is relevant. But security, login tracking, access history, none of that. This is not the answer. Option B, Governance Viewer. Now this one is interesting because governance and security can feel related, and they are in some ways. But in Snowflake's role model, Governance Viewer is focused on data governance artifacts, things like data classification tags, masking policies, row access policies, and related metadata. It's about how data is protected and classified, not about who's logging in and what they're accessing. Broader than Object Viewer, but still not the right answer here. Option D, Usage Viewer. This role is all about performance and cost, query execution times, warehouse credit consumption, storage usage, the kind of data your operations team and your FinOps team care deeply about. Useful? Absolutely. Security related? Not at all. Wrong answer. Which leaves us with option C, Security Viewer. And yes, this is the correct answer, and I want you to really understand why. Security Viewer in Snowflake gives access to the security-related subset of account usage views. We're talking about things like login history, who logged in, when, from where, whether it succeeded or failed. Access history, what data objects were accessed and by whom. Session information. Grant level details. This is exactly the data that your security and compliance teams need to do their jobs, to detect anomalous login behavior, to prove to an auditor that only authorized users accessed sensitive data, to investigate a potential breach. And the reason this matters so much in a certification context is that Snowflake is used by enterprises that have to meet very strict compliance requirements, SOC 2, HIPAA, GDPR, PCI DSS, you name it. The security viewer role is a core part of how those organizations implement controlled access to audit data. Understanding it means understanding enterprise data governance. So lock this one in. Security viewer is the role that controls security-related account usage views. The answer is C. All right, moving right along. Let's look into question 2. And I'm going to be honest with you, this one is legitimately tricky. Not because the concepts are impossibly hard, but because there are some very convincing wrong answers mixed in with the right ones. This is a multi-select question. That means there could be 2 correct answers, 3, maybe more. You need to pick every statement that is true. Question 2. Which statements correctly describe directory tables and their role in stage replication? Please choose 3 correct answers. Here are your 5 options. Option A, files greater than 5 gigabytes may cause failures. Option B, internal stages always replicate files fully. Option C, directory tables index files for replication consistency. Option D, external stages replicate only metadata, not files. Option E, directory tables are optional after enabling replication. Go ahead, read them again. Which ones sound right to you? Which ones make you second guess yourself? Pause the video here. Think and choose the right answer. Now, this one's really interesting, and here's why. Directory tables are one of those features that people tend to skim over when they're studying. They're not as flashy as virtual warehouses or as intuitive as tasks and streams, but they're genuinely important, especially when you start thinking about business continuity, failover scenarios, and reliable data ingestion pipelines. Let me give you a quick foundation before we go through the options. A directory table in Snowflake is essentially a metadata catalog for files stored in a stage. When you have a stage, internal or external, and you want to track which files are there, what their names are, what their sizes are, when they were last modified, you enable a directory table on that stage. It keeps that information up to date, and it becomes critical when you're doing things like stage replication across accounts. Now let's go through all 5 options. Option A, files greater than 5 gigabytes may cause failures. This one is true, and this is something that catches people off guard because we're used to thinking of Snowflake as this massively scalable platform that handles enormous data sets, and it does. But at the file tracking and synchronization level, very large files, specifically those above 5 gigabytes, can create issues during replication and directory table refresh operations. There are limitations in how the metadata tracking mechanisms handle files of that size, and it can lead to failures or inconsistencies. So this statement is correct. Option B, internal stages always replicate files fully. This one is false. And I want you to pay close attention to that word always, because that's exactly where the trap is. It sounds reasonable, right? If you're replicating an internal stage, you'd expect the files to come along for the ride. But that's not guaranteed. Whether files actually get replicated depends on your specific configuration, and in many setups, only the metadata and stage definition are replicated, not the actual file contents. The word always makes this an incorrect statement. Option C, directory tables index files for replication consistency. This one is true, and this is really the heart of what directory tables are about. When Snowflake needs to replicate a stage, it needs to know what files exist, where they are, and whether they've changed. That's exactly what the directory table provides, a reliable, up-to-date index of file-level metadata. Without this index, replication would have no consistent way to track the state of files across accounts. Directory tables are the foundation for file-level consistency during replication. Option D, external stages replicate only metadata, not files. This one is true. And once you understand what external stages actually are, this makes complete sense. An external stage in Snowflake is a named reference to a location in your own cloud storage, your S3 bucket, your Azure Blob Storage container, your Google Cloud Storage bucket. Snowflake doesn't own those files. It can't move them. When you replicate an external stage, what gets replicated is the stage definition, the URL, the credentials, the configuration. The actual data files stay exactly where they are in your cloud storage. Snowflake is just pointing at them, and that pointer gets replicated. Option E, directory tables are optional after enabling replication. This one is false. And this is probably the most dangerous wrong answer on this list because it sounds logical. You might think, once replication is set up and running, the directory table has done its job. I don't need it anymore. But that's not how it works. If your replication behavior depends on file tracking, which it does in most real-world ingestion pipelines, the directory table needs to stay enabled throughout the lifecycle of that stage. Disabling it can break file-level replication and lead to silent data consistency issues after a failover event. The consequences of getting this wrong in production can be really painful. So the correct answers are A, C, and D. The big picture: directory tables are not optional infrastructure. They're an essential metadata indexing mechanism that underpins reliable stage replication in Snowflake. If you're building data pipelines that need to survive failover events, you need to understand this thoroughly. Great, question 3 is up next, and we're staying in architecture territory, but shifting to a topic that comes up constantly in analytics engineering: materialized views. This is another multi-select. Multiple correct answers possible. Question 3, which characteristics apply to Snowflake materialized views? Please choose correct answers. Your 5 options. Option A, disables base table access. Option B, supports repeated query optimization. Option C, stores pre-computed results. Option D, eliminates storage cost. Option E, automatically refreshes data. Take a moment and think about what you know about materialized views. What are they? What do they do? What are their trade-offs? Pause the video here, think and choose the right answer. This part's super important, especially if you're going to be doing any kind of analytics, engineering, or data modeling work in Snowflake. Materialized views are one of those features that sound simple on the surface, but have a lot of nuance when you dig into them. And the exam loves to test that nuance. Let's start with what a materialized view actually is, because I want to make sure everyone is on the same page. A regular view in Snowflake is essentially a saved SQL query. Every time you query that view, Snowflake runs the underlying SQL fresh against the current data. It's like an alias for a query. A materialized view, on the other hand, actually executes that SQL and stores the result. The computation has already been done. The output is sitting there in Snowflake storage, pre-built and ready to serve. With that in mind, let's go through the options. Option A, disables base table access. This is false, and it's pretty definitively wrong. Materialized views are independent objects in Snowflake. They don't affect the underlying base table in any way. The base table remains fully accessible for reads, writes, and updates. Anyone who needs to query the base table directly can continue to do so, completely unaffected by the existence of a materialized view on top of it. This is just a wrong statement. Option B, supports repeated query optimization. This is true, and this is actually one of the primary use cases for materialized views. Think about a business dashboard that refreshes every 15 minutes, or a reporting query that gets run hundreds of times a day by different users. Without a materialized view, every single one of those executions triggers the full computation, the joins, the aggregations, the full table scans. With a materialized view, the result is built. The query gets served almost instantly from the stored result. That's a massive performance win for workloads that repeat the same analytical patterns. Option C, stores pre-computed results. This is true. This is literally the defining characteristic of a materialized view. It physically stores the output of the query. This is what makes it different from a regular view. The pre-computed result is stored in Snowflake, taking up storage space, but ready to be read without any computation overhead. This is correct. Option D, eliminates storage cost. This is false, and this is almost exactly backwards from the truth. Materialized views don't eliminate storage cost. They add to it. You're storing an additional copy of data, even if it's derived or aggregated. Yes, the aggregated data might be much smaller than the raw data, but you're still storing something extra. The trade-off with materialized views is always you pay more in storage and compute maintenance overhead, but you gain faster query performance. There's no free lunch here. Option E, automatically refreshes data. This is true. This is a key feature that distinguishes Snowflake's materialized views from a simple cached result. When the underlying base table gets new data through inserts, updates, or deletes, Snowflake automatically detects those changes and updates the materialized view to stay in sync. You don't have to manually trigger a refresh. This does incur some compute overhead because Snowflake has to do work to maintain the view, but it means your materialized view is always reflecting the current state of the data. That's really important for accuracy in analytical workloads. So the correct answers are B, C, and E. What's the mental model you should take away from this? Materialized views are a performance for cost trade-off. You get faster repeated query execution, stored pre-computed results that stay automatically refreshed, but you pay for it in additional storage and compute overhead. They don't block access to anything, and they don't magically eliminate costs. They redistribute the compute cost from query time to maintenance time. Let's move on to question 4, and this one is going to give us a chance to talk about one of the newer and more exciting parts of the Snowflake platform, Snowflake notebooks and the infrastructure behind them. Single correct answer for this one. Here's the question: which runtime environment is used for Snowflake notebooks Python execution? There is one correct answer. 4 options. Option A, database runtime. Option B, local machine runtime. Option C, containerized runtime. Option D, browser runtime. Think about how Python execution actually works in Snowflake notebooks. Where is the code running? What's doing the heavy lifting? Pause the video here. Think and choose the right answer. You might be wondering why this even matters. Why does it matter where the code runs as long as it runs? And that's actually a great question. The answer is that the runtime environment determines what kinds of workloads are possible, how they scale, what dependencies you can use, and how isolated and secure the execution is. Understanding the architecture helps you understand what you can build with it. Let's go through the options. Option A, database runtime. False. Databases in Snowflake are data storage and query execution layers. They handle SQL operations. They're not general-purpose compute environments for executing Python code. When you write a Python cell in a Snowflake notebook, a database is not what's executing it. This is a distractor. Option B, local machine runtime. False. This one is categorically wrong from an architectural standpoint. Snowflake is a cloud service. When you open a Snowflake notebook in your browser, you're interacting with Snowflake's cloud infrastructure. Your laptop is the client. It's the terminal you're using to communicate with Snowflake. The actual code execution happens on Snowflake servers, not on your machine. Nothing changes on your local system when you run a Python cell. Option D, browser runtime. False. This is a reasonable sounding answer if you're not familiar with how web-based notebooks work, but it's wrong. Your browser renders the UI, it displays the notebook, accepts your input, shows you the output, but it doesn't execute Python. That happens in Snowflake's backend infrastructure. If execution happened in the browser, you'd be extremely limited in what you could do. No heavy compute, no GPU access, no large-scale data processing. Option C, containerized runtime. True. This is the correct answer, and it's actually a really sophisticated piece of engineering when you understand how it works. Snowflake notebooks execute Python code inside containerized environments that are managed by Snowflake through a feature called Snowpark Container Services. When you run a Python cell, Snowflake provisions a container with the appropriate dependencies and runtime environment, connects it to a compute pool, which is a set of virtual machine nodes that provide CPU or GPU resources, runs your code, and streams the output back to your browser interface. The beauty of this architecture is the isolation and scalability it provides. Each notebook can have its own containerized environment with its own dependencies. You can do serious data science work, training machine learning models, running large pandas operations, even GPU-accelerated deep learning, all within Snowflake without managing any of the underlying infrastructure yourself. Snowflake handles the container lifecycle, the resource allocation, the scaling, all of it. This is a significant part of Snowflake's push to become a unified platform for both data warehousing and data science. You don't have to export your data to a separate environment to do your ML work. You can do it all in Snowflake in a notebook using the same data that's already in your Snowflake account. The answer is C, containerized runtime. And remember the key component, Snowpark Container Services and compute pools. All right, we are on question 5 now, and we're pivoting to the operational side of Snowflake, specifically how you monitor what's happening with your virtual warehouses. This is a single answer, multiple choice. Which Snowflake interface provides warehouse load graphs and query queuing insights in the Snowsight platform? There is one correct answer. Your 4 options. Option A, query history page. Option B, billing overview dashboard. Option C, user management console. Option D, warehouse activity section. This one is testing whether you know the Snowsight interface, Snowflake's modern UI, and specifically which section gives you compute monitoring capabilities. Pause the video here, think and choose the right answer. So let me give you some context on why this matters. Imagine you're a Snowflake administrator. It's Monday morning, users are coming in, running their dashboards, kicking off their ETL jobs, and then you start getting Slack messages. Queries are slow, things are timing out, the dashboard is not loading. Where do you go? What do you look at? The answer to that question is what this question is testing. Option C, user management console. This is very clearly wrong for this scenario. User management is where you create users, assign roles, manage authentication settings. It has absolutely nothing to do with warehouse performance or query monitoring. If you're here trying to figure out why queries are slow, you took a very wrong turn. Option B, billing overview dashboard. This one is tempting for a moment because you might think credit consumption relates to warehouse activity, and it does in a loose sense, but the billing overview is focused on cost, how many credits you've consumed, what your spending trends look like, how costs break down by warehouse or service. It's a financial reporting interface, not an operational monitoring interface. It won't tell you about real-time query load or queuing. Option A, query history page. Now this one is more interesting because it genuinely does relate to performance. Query history gives you a detailed log of individual queries that have run in your account. You can see duration, status, SQL text, the warehouse it ran on, bytes scanned, and so on. If you want to investigate a specific slow query, this is a great place to start. But the key thing is that it's query level. It's about individual queries. It doesn't give you a warehouse level view. No load graphs, no time series visualization of concurrency, no view of how many queries are queued up at any given moment. Option D, warehouse activity section. This is the correct answer, and this is the section you'd naturally navigate to when you want to understand the health and load of your virtual warehouses. The warehouse activity section in Snowsight gives you a visual time series representation of warehouse load. You can see how many queries are actively running at any point in time, how many are queued up and waiting, how the different clusters within a multi-cluster warehouse are being utilized. It's designed specifically for the kind of operational monitoring that administrators and engineers need to do capacity planning, identify bottlenecks, and optimize warehouse configuration. When you're staring at that section and you see a spike in queued queries at 9 a.m. every day, you know you have a concurrency problem during morning peak hours. When you see consistently low load with slow query execution, you know something else is going on. We'll talk about that in question 6. The point is, warehouse activity gives you the context you need to make informed decisions. The answer is D, warehouse activity section. If you're managing Snowflake in production, bookmark that section in Snowsight. You'll be visiting it often. We've made it to question 6, and I saved this one for last because it's my favorite kind of question. A real-world scenario that tests your ability to diagnose a problem and choose the right solution. Single correct answer. Here's the scenario. An analytics team is investigating slow query performance on a warehouse. The load monitoring chart shows a running query load of 0.15 and no queuing. Based on this observation, what action should the team take to improve query performance? There is one correct answer. Here are your 4 options. Option A, resize the warehouse to a larger size to provide more compute resources. Option B, increase min cluster count for the warehouse. Option C, decrease the auto-suspend timeout to reduce idle credit consumption. Option D, start a second warehouse and split the workload between 2 warehouses. Now I want you to really read that scenario before you answer. There's a running query load of 0.15, no queuing, but queries are slow. What does that picture tell you? Pause the video here. Think and choose the right answer. Let's break that down together because this question is genuinely testing diagnostic thinking, not just factual recall. First, let's make sure we understand what the numbers mean. A running query load in Snowflake represents how busy the warehouse is relative to its capacity. A load of 1.0 means the warehouse is fully saturated. A load of 0.15 means it's running at about 15% capacity. And no queuing means no queries are waiting. They're all getting started immediately. So let's paint the picture. The warehouse is barely being used. No queries are piling up, but somehow the queries that are running are slow. That is a very specific diagnostic signal, and if you understand it, the answer becomes obvious. Option D, start a second warehouse and split the workload. This is a classic concurrency solution. If you had 100 concurrent queries all hammering the same warehouse, splitting them across 2 warehouses would help each warehouse handle a more manageable load. But look at your load number, 0.15. You don't have a concurrency problem. You barely have any queries running. Splitting the workload would give you 2 warehouses, both running at around 8% capacity, and your queries would still be just as slow. Wrong answer. Option B, increase min cluster count. This one is also a concurrency solution. Min cluster count controls how many clusters are always running in a multi-cluster warehouse, ensuring capacity is available for concurrent workloads. But again, no queuing, low load. Concurrency is not your problem. Increasing clusters would cost you more money and do nothing for your slow queries. Wrong answer. Option C, decrease the auto-suspend timeout. This is purely a cost management move. The auto-suspend timeout determines how long the warehouse sits idle before it shuts down and stops consuming credits. Reducing this timeout saves money when the warehouse isn't being used, but it has literally zero impact on query execution speed. If your queries are slow now, they'll be just as slow with a shorter auto-suspend timeout. Wrong answer. Completely different domain. Option A, resize the warehouse to a larger size. This is the correct answer, and here's the insight that makes everything click. A low running load does not mean you have enough compute power for your queries. It means you don't have many queries running simultaneously. Those are 2 different things. Imagine you have a small warehouse running a very complex query. Maybe it's doing a massive join across several 100 million rows, or it's running a window function over a huge data set. That query might be consuming every bit of CPU and memory available in that warehouse. But if it's the only query running, the load number will look low because the warehouse isn't juggling many concurrent queries. The bottleneck isn't concurrency, it's raw compute capacity for each individual query. When you resize the warehouse to a larger size, you're adding more compute nodes, more CPU, more memory, more parallelism for individual query execution. Larger warehouses can process more data simultaneously within a single query, which directly improves execution speed for complex, resource-intensive queries. This is the documented Snowflake best practice, and it's worth memorizing the logic. Low load plus slow queries equals a compute bottleneck. The fix is to resize up. High load or queuing plus slow queries equals a concurrency bottleneck. The fix is to add clusters or split the workload. The answer is A, resize the warehouse. All right, we are done. 6 questions, 6 deep dives. Let me give you a clean summary before we wrap up because this stuff is worth reviewing one more time. Question 1, the role that controls security-related account usage views is Security Viewer. It provides access to login history, access history, and other audit data. Object Viewer is for object metadata, Governance Viewer is for policy and classification data, and Usage Viewer is for performance and cost data. Question 2. The correct statements about directory tables and stage replication are that files over 5 gigabytes may cause failures, directory tables index files for replication consistency, and external stages replicate only metadata. Internal stages do not always fully replicate files, and directory tables are absolutely not optional after enabling replication. Question 3. Materialized views store pre-computed results, support repeated query optimization, and automatically refresh when underlying data changes. They do not eliminate storage costs, they add to them, and they do not restrict access to the base table in any way. Question 4. Snowflake notebooks execute Python code in a containerized runtime environment managed through Snowpark container services and compute pools. not local machine, not browser, not database runtime. Question 5. Warehouse load graphs and query queuing insights in Snowsight are found in the warehouse activity section, not query history, not billing overview, not user management. Question 6. When you see low running load combined with slow query performance and no queuing, the problem is compute capacity, not concurrency. The correct action is to resize the warehouse to a larger size. Adding clusters, splitting workloads, or adjusting auto-suspend are all solutions to different problems. These 6 questions touch on concepts that appear across multiple Snowflake certifications: the SnowPro Core, the SnowPro Advanced Data Engineer, the SnowPro Advanced Architect, but more importantly, they touch on things you'll actually encounter and need to understand in real production Snowflake environments. Security governance, replication reliability, performance optimization, these aren't just exam topics. They're the stuff of day-to-day data engineering life. So if you got all 6 right, that's awesome. You're clearly putting in the work and it's paying off. If you missed a few, that's completely fine. That's exactly what practice questions are for. Go back, review the explanations, make sure you understand the reasoning, and quiz yourself again in a few days. If you found this video helpful, please go ahead and like it. It genuinely helps this content reach more people who are on the same certification journey as you. And drop a comment below and let me know, which of these 6 topics do you want a deeper standalone video on? Security roles, stage replication, warehouse tuning. I read every single comment and I use them to plan future videos. If you're not subscribed yet, hit that button. We've got a ton more Snowflake content coming and you don't want to miss it. Thanks so much for watching all the way through. I know this was a long one, but you made it. And that says a lot about how serious you are about this. Keep studying, keep building things, and I will see you in the next one. You've got this. Before I let you go, I want to take a step back and talk about something bigger: the mindset behind studying for technical certifications like Snowflake. Because I've seen a lot of people approach certification prep the wrong way, and I want to make sure you're not falling into those traps. The biggest mistake people make is memorizing answers without understanding the reasoning. You can memorize that security viewer is the answer to question 1. You can memorize that the answer to question 6 is resize the warehouse. But if you show up to the exam and Snowflake phrases the question slightly differently, maybe they describe a scenario instead of asking directly, and you only memorize the answer, not the concept, you're going to struggle. The approach I always recommend is to understand the why deeply enough that you could explain the concept to a colleague who has never used Snowflake before. If you can teach it, you understand it. And that level of understanding will serve you not just on the exam, but in every Snowflake project you work on for the rest of your career. Let me give you an example using something we covered today. With materialized views, the surface level answer to what is a materialized view is it stores pre-computed results. That's true, but the deeper understanding is the trade-off. You're paying a storage and compute maintenance cost now at data change time to avoid paying a compute cost later at query time. That trade-off is the thing that helps you decide when to use materialized views in a real project. When do you use them? When the same expensive computation runs repeatedly, dashboards, hourly reporting, repeated aggregations. When don't you use them? When the data changes extremely rapidly and the maintenance overhead outweighs the query performance benefit. When queries are not repeated frequently enough to justify the storage cost. That level of nuance, understanding not just the what, but the when and why, that's what separates someone who just passed the exam from someone who actually knows Snowflake. Similarly, with the warehouse tuning scenario from question 6, the surface level answer is low load and slow queries means resize. But the deeper understanding is the mental model for diagnosing warehouse problems. You're essentially reading signals from the load monitoring chart and asking, is this a concurrency problem or is this a compute capacity problem? Queuing and high load point to concurrency. You need more clusters or a second warehouse. Low load with slow queries points to compute. You need a bigger warehouse. No load at all and things are still slow might point to something else entirely. Maybe the data isn't being cached properly. Maybe there's a query design issue. Maybe the table statistics are stale. Understanding the diagnostic framework means you can handle variations you've never seen before. And that's the real value of going deep on these practice questions, rather than just skimming through to the answers. Every question is an opportunity to build a piece of mental infrastructure that will help you think more clearly about Snowflake in any context. I also want to quickly touch on the area of stage replication and directory tables because I know it can feel abstract if you haven't worked with it hands-on. Here's a concrete way to think about it. Imagine you have a primary Snowflake account in the US and you're setting up a secondary account in Europe for disaster recovery. You have internal stages where files land before being ingested into Snowflake tables. If the primary account goes down and you need to fail over to the Europe account, you need the secondary account to know about all the files that were in those stages. Were they ingested? Which ones are still waiting? Without directory tables, that information isn't reliably available in the secondary account. With directory tables enabled and replicated, the secondary account has a complete up-to-date index of what files exist and in what state. Failover works cleanly. Ingestion pipelines pick up right where they left off. That's the real-world scenario that makes directory tables matter. And with Snowflake notebooks, think about why containerization matters. Before cloud-native notebook environments existed, data scientists had to download data from the data warehouse, load it into a local Jupyter notebook, do their analysis and modeling, and then somehow get the results back into the data warehouse. That process was slow, it was error-prone, it created data movement risk, and it meant the data science environment was completely disconnected from the data platform. Snowflake notebooks running in containerized runtimes solve this elegantly. The code runs where the data lives. You're not moving data out, you're moving compute to the data. That's a fundamental architectural shift, and it's why the containerized runtime architecture matters. I hope this broader perspective helps contextualize why these aren't just exam questions. They're windows into real engineering problems and real architectural decisions that Snowflake has made to serve enterprise data teams. All right, I've genuinely said everything I wanted to say today. Leave me a comment, let me know how you did on the practice questions before you saw the answers, and what surprised you most from the explanations. I love hearing how people think through these problems. Like the video if it helped, subscribe if you want more, and I'll see you next time. Take care, keep learning, and go build something great.